In this experiment, I'm testing the relationship between height and time for objects rolling down an incline. So really it's more of the proportion between the distance and the y value and the overall distance that it travels. What I'm doing is I have a large ladder that I have a 45-inch piece of wood propped up against at different angles, and I roll down a Matchbox car and record how long it takes it to roll down the incline depending on the height that I've propped it up against. The dependent variable in this experiment would then be the velocity or the time, depending on how I graph it. And the independent variables would be the h value, it would be the overall distances traveled, and so forth. In order to conduct this experiment, the first thing I need to do is prop up the wooden plank up against the ladder and record the height. Then I'll take the Matchbox car, I'll set it at the very, very top of the plank, and then I'll record how long it takes to get to the bottom. I'll then move the plank up to a different position, different angle, record that new height, again put the Matchbox car at the top of the plank and record how long that takes, and continue that with every height. If the experiment goes as expected, the height and the time should have some sort of inverse relationship, because as the height increases, more of the gravitational force will be able to act to accelerate the object in the y direction, therefore increasing the speed and decreasing the time. Okay, to start out the experiment, we're going to start at the lowest height, which is 11.5 inches. And I'll start the stopwatch when I'm up here, and I'll stop it when it's down at the very bottom of the ramp. And that was 1.42 seconds. Okay, this is 22.25 inches. And just like the last trial, I'll start the stopwatch when it's right here, and I'll stop it at the bottom. It's the same plank, so it's the same distance, but different height. That was 1.09 seconds. This is the sixth and so far lowest trial at only 4 inches off the ground. As you can see, it's very low. Hopefully the little Matchbox limousine, very classy, will make it to the end of the wood, but I'm not super confident that it will be able to. So let's see what happens. As you can see, it essentially does not really go anywhere. It can't really overcome the static friction of the wood, because as it is not a perfect experiment, there is friction that sometimes the Matchbox cars can overcome, so this trial will not be able to be counted. This is the data I gathered from those trials. I didn't have a meter stick, so I had to record them in inches, but I multiplied the inches by 0.0254 in order to convert to meters, so it should be fairly accurate still. As you can see, as the height increases, the time did decrease, and I explained that in the third column, where I showed how as you increase the height, it has more potential energy, and due to the conservation of energy, having more potential energy at the top will give it more kinetic energy at the bottom, and because kinetic energy is 1/2 mv squared, it'll have more velocity and take less time to get there. I found the potential energy by multiplying mgh, which is mass times gravity times height. I didn't have the mass of the car, so I did do it in terms of m, but it's still proportional because the m's not changing with having the same object. This is the graph of the data I collected from the experiment. As you can see, the time, which is the x-axis in seconds, and the height, which is on the y-axis in meters, have some sort of inverse relationship. So they're not completely proportional to one another either, otherwise the graph would be linear, which it is obviously not. The height is in meters, not in inches, but because the inches were all converted with the same conversion factor to meters, it shouldn't make a big difference. And I'll show you the true relationship with the linearized graph on the next slide. This is a linearized graph of the data and the graph I just showed you, with time once again being on the x-axis, and this time height squared is on the y-axis, and that is how you make them proportional to each other to linearize them, where time is equal to height squared, or you could also say it as height is equal to the square root of time. I did have to remove the 6th data point because it was an outlier, and in order to get a better line of best fit, I had to remove it. These findings do make sense because if you're discussing the conservation of energy when it comes to these findings, MGH, which is all the potential energy it has at the beginning, is equal to 1/2 mv squared, all the kinetic energy it has at the bottom. So in that scenario, height is equal to velocity squared, and because distance over time is velocity, that would make sense that height and time have a similar relationship. I'm going to wrap up this experiment by explaining sources of error and improvement and briefly going over my findings once again. A lot of the sources of error came from the friction of the wooden plank that I used, because that is going to affect how fast that the thing is moving, and it's going to affect the time. I didn't have a meter stick, so I had to convert all of those the heights into meters after recording it in inches, so that was another potential source of error. I didn't have any special equipment at home for properly recording how long it took to get to the bottom. I just had a phone stopwatch, so that is another source of error. A lot of those sources of error just came from lack of proper materials, such as I mentioned before. I didn't have anything like a photo finish, I didn't have a meter stick, there is friction, so those are all things that come from just doing this project at home. Ways that I can improve this in the future is perhaps doing more trials, like getting a longer piece of wood and trying out more angles so I can have more data points and reduce any error that comes from that. That will probably improve it in the future, and things like that. Perhaps getting a meter stick in order to better record the data would also help. So to wrap it all up, the final conclusion I reached between the relationship of height and time on objects that are rolling down an incline is that time is proportional to the height squared. And that is my findings. Thank you for watching.